6-2 in college algebra, talking about characteristics of polynomial functions. The very first thing talks about end behavior. You did a little bit of it in Algebra 2. We are now a little more knowledgeable. There's two things you need to know about. You need to know about the degree, and you need to know about the leading coefficient. Right? So you can see here that this guy, the degree, this is y equals x squared, the degree is even. Any even degree polynomial, the two ends will be going the same direction. Aren't those both going up? Right? Now, why would that be going up? Because it's about the leading coefficient. Remember where you'd look at the a value and see, does this open up or does this open down, right? What kind of number would the a value be if this parabola opens up? Positive. So that's why this says you've got a positive leading coefficient, the a value is positive, and that's got an even degree. This guy here, I also know is an even degree polynomial because the ends are going the same direction. But since this guy opens down, that means the leading coefficient is negative. You cool with that concept? Those are the easy ones. The even ones, because we're so used to parabolas, you know, it's like, okay, I understand when a parabola opens up and when a parabola opens down. Even if it was a fourth degree polynomial or something, it could look like this. You know, a lot of fourth degrees make a W type shape, but do you look at the ends, right? Do you see that they are going the same direction, right? So that means it's got an even degree, and the leading coefficient is positive because they're going up. If you had like a fourth degree polynomial that looks like this, that's still an even degree because the ends are going the same direction, but it's going down, so the leading coefficient is negative. It's about those odd degree polynomials. We're not very used to graphing those, at least from the Algebra 2 standpoint. The cubics or the fifth power or the seventh power, they look like the snake, right? Meaning the ends are going different directions. One of these guys is going up, one of these guys is going down. So how do you know, since they go different ways, like which one's which? Like it's all about the leading coefficient. If the leading coefficient is positive, I just have a stupid little phrase that I remember. I don't know what Mrs. Colwell may have taught you guys, but I say odd means they got to go different directions, and positive means that upright. I just say if you're positive, you're up, right? Positive, like if your attitude is positive, your attitude is up, and it's upright because if you look to the right, isn't this thing going up as it goes to the right? Positive, you got an upright, and then you've got a down going that way. If the leading coefficient is negative, you do not have this thing going up as you go to the right. It goes up as you go to the left, and this goes up, down. So positive is up to me, and upright, like you're standing straight up and down. So positive, upright is the way I remember those. So very simple things that they're asking us here on these first four problems. They say, what is the end behavior for each one of these polynomials? You used to describe it as x approaches infinity, f of x approaches negative infinity, or something like that. We will not be doing that. We will make a little sketch of these situations. First thing you got to do, though, again, remember your assignment will be on paper, is I want you to circle the guy that makes this degree. Like, who's the guy in this dude with the biggest degree? Isn't that him, right? That's him. That is an even degree, correct? So what does that mean about your ends? Same way or different ways? Same way. Look at the coefficient in front of them. It is positive, right? It's a positive 1. So same way, go in which direction, up or down? So all you do is you sketch this. These are the two ends. Leave the blank as a gap, you know. Those are arrows. Let me try that one more time for you. You just sketch that the left end is going up and the right end is going up. And I don't know what's going on in the middle. There could be all kinds of squiggle crap going on in the middle. This is the end behavior. Up, up. Rock and roll. Next guy. Circle the guy with the biggest degree. They will be written out of order, right? So you got to go in there and find them sometimes. That guy is the biggest degree. Even or odd? Odd. Different directions, correct? How do you know which one? You look at the coefficient. If he is positive, positive is upright. Positive, upright. So upright, that means down left then. Correct? Cool with that? Next guy, biggest degree. This dude. Even, same direction. Negative coefficient mean we're going down in both directions. So that's all they'll ask you for on your homework is little sketchies like that. And finally, biggest degree, 7, odd different directions. Since the leading coefficient is negative, negative is not up, right? Negative is the opposite of that. Right? Don't go up right, go up left. Okay? It's the only way that I remember it. If you have a better trick, then kudos to you. Before we do all this, I think when she typed out these worksheets, sorry that I didn't put it ahead of time, if you skip to the next page, we need to kind of talk about this first. It just kind of didn't fit on that page. I think she put it over here, and then we got to flip back, you know. So what we're looking at is the zeros of a polynomial, and their x-intercepts is where it touches the x-axis or crosses the x-axis. Well, one thing that we're not very used to is called a point of tangency. You may remember the word tangent from geometry class. When a line is tangent to a circle or something, it just touches it in one place. Here's like part of your graph right here, and here's the x-axis. That red thing touches the x-axis in one spot, this point of tangency. So when they're asking us on the previous page, like where's the points of tangency, where's all this stuff at, this is what they're talking about, where the graph touches the x-axis but does not cross the x-axis. And what happens there is when we find our roots, we get multiple roots there. Right? So like if this was at -1 on the x-axis, that means that we've got a multiplicity of 2 for a root there at minimum. We'll talk about that later. So let's go back to the first page right here. There's all kinds of other, I shouldn't say first page, but this particular page, all kinds of other things they want to talk about. Absolute minimums and absolute maximums. There's a similarity yet a difference to those. Absolute minimum means, is there a point on the graph that is the lowest possible place it could be? Like, is there a spot where it never gets lower than that? So let's just look at this graph right here. How low does it go? Negative infinity, which that is not really a number that we can compute, right? So is there an absolute minimum to this graph? Like, is there a real number that you can actually find that this goes as low as possible? No, because this goes to negative infinity. So does this have an absolute minimum? There are none. This has no absolute minimums whatsoever. Cool, that's absolute. Absolute max means go as high as you can possibly go. Is there a place that's as high as you can possibly go? Well, you can see that since this has got, take a wild guess. What kind of degree does this have, even or odd? That's an even degree. There will be some sort of absolute, either minimum or maximum, because this guy's got to go down to negative infinity both ways that way. Won't there be a highest possible point out of these? So it looks really close that like A and C are at the same level. I think C is just a little bit higher than A, though, the way it's drawn. So would you believe that C is the highest point on this entire graph right here? So absolute maximum is at C. That's all they're asking. Like, list on this graph where these are at. There's one here at C. Those are absolute. As high as you can go, as low as you can go. Absolute. Different than relative minimums. Relative minimums are where there's any kind of turning points, or same thing as relative max. What do I mean by a turning point? Where the graph goes from like increasing to decreasing, or vice versa. If I was to trace this graph, isn't my green highlighter going up, 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 up? It's increasing, correct? Then right there at A, doesn't it all of a sudden start to decrease, correct? There is a turning point there. So this is either a relative maximum or a relative minimum. What does it look like to you, max or min? That is a relative maximum. So relative max here at A. Are there any other relative max? Is there any other places where that happens? It does happen at C. People are like, hey, but C was the absolute max. You're right. It was the absolute max. It is also a relative max, right? You got to list it again. It does happen there. There is a maximum there, a relative maximum. Were there any relative minimums? A place where it goes from like decreasing to increasing on this graph. B, right? There is a relative minimum there. It is not the absolute minimum of the graph, but it is a place where things bottom out and then it changes around. There is a turning point there. Cool with absolute versus relative. Number of x-intercepts. Well, let's count it up, baby, if my eraser would work. Number of x-intercepts is where it crosses the x-axis at, so that would be 1, 2, 3, 4 of them. Correct? Isn't there 4 x-intercepts? Are there any points of tangency? That's what we talked about. That's on that next page, where the graph touches the x-axis, but it never crossed the x-axis. So you touch the x-axis here, but then that thing, whoop, go right across it. It went across it. It went across it. It went across it. Are there any points of tangency on this? So there are none. Don't put 0, or I guess you should put 0 is what I meant to say. You should put 0 instead of none because they're asking for the number of points of tangency, so there are 0 of them. I really wouldn't mark you wrong if you put none, but to answer the question correctly. Number of turning points. How many turning points? What do you think? Is A a turning point? Yes. Is B a turning point? So where it goes from increasing to decreasing or decreasing to increasing. And is C a turning point? How many turning points? 3 turning points. So here's the idea behind minimum degree. You might make a note somewhere off to the side. The minimum degree is turning points plus 1. However many turning points you have, you always add 1 to that, and that will be the minimum degree possible. Turning points plus 1. How many turning points did we have? 3. Add 1 to it. What's the minimum degree? 4. Then you better double check for making sense. 4 is an even degree. Is this graph an even degree graph in behavior? It doesn't mean that this is a 4th degree polynomial. It could be a 6th. It could be an 8th. It could be a 10th. But the minimum possible degree is a 4 degree polynomial. Let's try the next one. Absolute min. First of all, the easy thing to realize is what kind of degree does this have, even or odd? It's got odd. That means that this guy's got to go down to negative infinity, correct? So there is none for an absolute minimum. Absolute maximum? None. Can't happen when you have an odd degree, because odd degrees go different directions, right? It's got to go up to infinity and down to negative infinity. That's called the range of this function, from negative infinity to positive infinity. Relative mins, do we have any? We're at A and C, right? You cool with A, comma C. Relative max, B and D. Down with those. X-intercepts, how many do you see? 1, 2, 3. Cool. Any points of tangency where that graph touches the x-axis but never crossed the x-axis? This touched it and crossed it. This touched it and crossed it. This touched it and crossed it. C, it does not touch the x-axis there at C. You with me on that? So we okay with that? So any points of tangency? 0. How many turning points are there? Turning points, all you got to do is add all these up. It's all your relative mins and all your relative maximums. Those are the turning points. So shouldn't there be 4 of them? That means the minimum degree of this puppy is what? 5th degree. Turning point plus 1. Does it make sense? 5 is an odd number. Is this an odd degree graph right here? Cool? Next. Absolute min. What kind of degree is this, even or odd? Even. So it better have some absolute, either mins or max. It's got to have one of them. Since this thing opens up, won't it have an absolute minimum? What is the absolute minimum? That's supposed to be an A right there, by the way. What is the absolute minimum of this graph? It's C. It's the lowest possible point you could have. Absolute max? None. Relative mins, A and C. Even though C is the absolute min, it is also a relative min because it's a turning point, and relative max is at B. Correct? Number of x, number of x-intercepts, deuce, points of tangency. That's the new thing to us. Are there any points of tangency where the graph touches the x-axis but does not cross it? There are 0 of them. Turning points, 3. Minimum degree, how do you figure that out? Turning points plus 1, 4. Does that match up even with even? Yep. Sweet. Try that one. This has got an absolute minimum at A, right here. It's got an absolute maximum. There is none. Relative min, also A. Relative max, there is none. X-intercepts, 1. Point of tangency, that is at point A right there. There is 1 because it touches the x-axis, but it never crossed it. That means the turning point is 1. Minimum degree is a 2 right there. That's even. That's even. Sweet. Again, all over the place. Absolute min, since that's an odd degree, will it have an absolute min? None. None. Relative mins, B and D. Relative max, A and C. Cool. X-intercepts, 1, 2, 3, 4, 5. Any points of tangency? None, 0. Turning points, count all these up, 4 of them. Minimum degree is a 5. It doesn't mean it's a 5th degree polynomial. It could be a 7th. It could be a 9th. It's got to be odd, but the smallest degree possible is a 5 right there. Sweet. And then, again, it's hard to see the arrows at the end, but that's an even degree. Absolute minimum looks like A. Absolute max, they try to trick you to thinking that F is the absolute max. F is not the absolute max because the arrows are continuing to go up. Relative min, A, C, E, G. Relative max, B, D, F. X-intercepts, 1, 2, 3, 4, 5, 6, 7. Points of tangency, are there any? At B, right, touches the x-axis, does not cross it, so there is 1. Turning points, 1, 2, 3, 4, 5, 6, 7. Minimum degree, 1 more than that, 8. I hope you found that easy. Did you find that easy? Those are the things you need to ask yourself when you do these problems. That's a setup right there. It's like you need to know how many x-intercepts. You need to know how many turning points. You need to know the minimum degree. If you can do those, then you do them mentally when we do the next type of problems. So back to this points of tangency thing, we are looking for x-intercepts and the roots to this. Anywhere there is a point of tangency, you get a root of multiplicity, right? The graph is always got to be of even multiplicity, so it could be multiplicity of 2, multiplicity of 4. That means that there could be 4 possible roots. I don't know if you remember back when you did synthetic division, and you'd find all the roots and all that stuff, and you'd have to synthetically divide. Well, we'll do that again. But any point of tangency, there's going to be multiplicity of roots right there. So consider this graph. Boom. It's an even degree, going up. Use the letter label to describe the intervals over where g of x satisfies the following conditions, where g of x is positive. Where is a graph positive at? Above the x-axis. Aren't all those numbers positive right there? So as an interval, where does it start from? If you go from left to right, where is this thing positive? From negative infinity, right, starts way up yonder, and you go all the way down to where? Well, A, right? You need the x value of it. The y value is 0, I'll give you that. But the x value of this point is at A. Does A count or not count? This point is on the x-axis. Is that positive when it's on the x-axis? What's the y value of that point right there? 0. Is 0 a positive number? 0 is neither positive nor negative. So does 0 count? So bracket or parenthesis? Parenthesis. This thing is positive in this interval from negative infinity up to A, not inclusive. Is there another interval where it's positive? So how do I put them together? Union. Where does it start from? E. Does E count? No, because it's on the x-axis. That's at 0, and it goes to infinity. That's where that thing is positive at. from negative infinity to a, not included, from e to infinity. So where's he negative at? All of this stuff, where it's below the x-axis, correct? Every y value up here is positive, every y value down here is negative, and every y value right here on the x-axis is 0, right? So where does it start from? A, not inclusive. Then there's just one green interval all the way up to E, not inclusive, from A to E. Noise? Where is this thing increasing? I'll erase. That's not an eraser. That's not an eraser. Where's this thing increasing at? Well, that's where you look from left to right where it's going up. Boom, boom. Would you agree with that's where that thing increases? Give me this interval from where to where? From B to C, not inclusive. Because it is not increasing at B, it is neutral there, right? It's not going down, it's not going up. And go to C, union, D to E. At infinity, thank you, my bad. D to infinity. Then, where's it decreasing? Exact opposite, the leftovers, from negative infinity to B, non-inclusive, union, C to D. Cool with that? That was from Unit 2. Yep. Now, mental thing. We'll have these for notes. This will really help. They're going to give you some graphs. Let's kind of put these notes down here of all the things that you would check for. So before we do 14 through 17, it says they want to know part A, B, C, D, E, F, G. These are the questions that they're asking you. All we got to do is answer them. They want to know if the leading coefficient is positive or negative. What would you look at to see if the leading coefficient is positive or negative? What do you look at? The arrows, right, which is called the end behavior, right? So put that as a note, things you're checking. You would check the end behavior, right? If the degree is odd or even, what else do you look at? The direction of the arrows. It's about the arrows, which is called the end behavior. Those two things, that's what you look at. I kind of do them in reverse order. First I look at the degree, then I look at to see if the leading coefficient is positive or negative. Is the constant term positive or negative? Let's go back a phrase. The constant term. What was so great about the constant term? He was really the y-intercept. So this y-intercept, isn't he 36? That's above the x-axis. What are you looking at for the constant term? You check the y-intercept. You check the y-intercept. The degree must be greater than or equal to what whole number? Or I shouldn't have said whole, but it is a whole number. The degree must be greater than or equal to what number? Back a couple pages ago when we found the minimum degree, right? How did we find the minimum degree? You would count the turning points plus 1. Number of turning points plus 1. The degree must be greater than or equal to what number? You count the turning points and add 1 to it. That's the minimum degree. How many distinct roots are there? That's an interesting word. Distinct roots. You can see them. Distinct roots. The roots, we've been trying for maybe 4 years now for you to get to understand what the roots are. The roots are the band on The Tonight Show, and also the roots are the x-intercepts, where that thing crosses the x-axis. When you solve a quadratic equation, you are finding the roots. So you count the x-intercepts, the number of x-intercepts. How many roots are there? You count the number of x-intercepts. How many roots have even multiplicity, though? Some of those roots, some of those x-intercepts are fancy, right? They're fancy. They have more than one root there because that was called a point of tangency. Right? That point of tangency, the points of tangency. And if you don't remember what points of tangency were again, you don't have to write all that down if you don't want to, but that's where the graph touches the x-axis but does not cross it. So the point of tangency will give you a root, but it will also mean that that root's there more than once, right? It's in even multiplicity. There could be 2 roots there. There could be 4 roots there. There could be 6 roots there. We'll get into that later. And then must there be imaginary roots, right? Roots, real roots cross the x-axis. Imaginary roots do not cross the x-axis. How do you know? Well, I kind of shortened this up. You just look to see if part E plus part F equals D, part D. Instead of writing all that stuff down, look to see if part E, the distinct roots, plus part F, the multiplicity, equals the degree of this thing. So just to make it short, because you'll have this in front of you, you look to see if E plus F equals D. The number of distinct roots plus the multiplicity equals your degree. If they're equal, then there's no imaginary roots. If they're not equal, then there's got to be imaginary roots. So let's put it into play. Here's all that stuff again. Here's this graph. We need to answer these questions. Is the leading coefficient positive or negative? Negative. You can abbreviate that neg. Leading coefficient is negative. Is the degree odd or even? Even. Is the constant term positive or negative? The constant term, again, is the y-intercept. This is the y-intercept. Is he above the x-axis or below the x-axis? So that is negative. Part D. Is the degree must be greater than or equal to what number, right? So what's the degree? We count the x-intercepts. Count the x-intercepts. How many x, oh, my bad, it's turning points plus 1. Sorry, I got a little distracted there. The degree must be greater than or equal to what number? Count the turning points. How many turning points? There's one, there's one, there's one. How many turning points do I have? 3. So the degree must be greater than or equal to what? 4. Turning points plus 1. Turning points plus 1. How many distinct roots are there? 2. How'd you get 2? That's the x-intercepts. Do any of those roots have even multiplicity? Like, are they multiple roots? If those x-intercepts were points of tangency, these red dots here, are they points of tangency? So it says, how many roots have even multiplicity? None. So must there be some imaginary roots? You take E, says we've got 2 real distinct roots, and we've got no multiplicity. Does that equal, if you add them together, does that equal your degree, yes or no? So must there be imaginary roots, yes or no? There has to be, because this plus this does not equal 4. You're supposed to have 4 roots possible on this thing, and I only see 2. Here's some imaginary roots in this crazy zone right here. It never went up and crossed the x-axis. So you look to see if E plus F, if you add them together, if it equals this, then you've found all your roots. They're real. Otherwise, they're not. Next, A, leading coefficient positive or negative? Odd or even? Even. Is the constant term positive or negative? That's the weird part. That's where you're looking for the the y-intercept. There it is. Positive or negative? Positive. Part D, is the degree greater than or equal to what number? Turning points. How many turning points? 3. Add 1. Get a 4, baby. Cool. Get a 4. Part E, how many distinct roots do you see? That's where they cross the x-axis. Or I shouldn't say cross. They touch the x-axis. How many places does it touch the x-axis? 2 times. Were there any points of tangency? Is this a point of tangency? Yes or no? So there's one of them. Is there another point of tangency? There's another one of them. How many points of tangency were there? 2. Must we have imaginary roots? 2 plus 2, does it equal 4? Since that means we've found all our roots, there are no imaginary roots. do 16. These parts you should have really no problem with. It is a positive because it's odd degree. I really answer B first, to be quite honest with you. It's odd degree. Upright is positive, leading coefficient. The y-intercept, the question is worded poorly. Should say, is the constant term positive, negative, or 0? It's actually 0. There are 7 turning points. Excuse me, 6 turning points. Add 1 to it, you get 7 for your minimum degree, which that better match what that is. Odd, right? Odd. Better be going different directions. 5 roots that you see. Do you see any turning points? Or excuse me, points of tangency. Point of tangency. Are any of those at a point of tangency? Nope. So must there be imaginary answers? Yes. And they're somewhere in this crazy zone right here. That thing wigged out on us. Yeah. Uno más. This is an odd degree. Since it's not going upright, it's got a negative leading coefficient. The y-intercept is right here in a positive position. 4 turning points plus 1 means it's got degree 5, minimum degree of 5. It doesn't mean it's a 5th degree. It's the minimum degree that it could be. 4 real zeros. There is a point of tangency, so that means, booyah, that you get your multiplicity roots. You have 4, 5 roots. Yay.